Well, thank you so much, Jeremy, for that kind introduction. I'm really excited to be here at ICFP. I've come to ICFP and Popple as well, where many of you go, a number of times in the past, but I haven't been in recent years. So what I've been doing in my meantime is kind of what I would like to tell you about with this talk on what I call compositional creativity. So. As Jeremy mentioned, I'm an assistant professor at NC State. I did a brief postdoc at the University of California in Santa Cruz, where I met the Expressive Intelligence Studio, which is a lab that works on applying artificial intelligence to creative applications and to enabling more expressivity in what people do with computers. And before that, I was a PhD student at Carnegie Mellon in the POP group. So. The conferences that I used to go to had many words that all of you are familiar with, functional types, logic, deduction, and languages. And the conferences that I've been going to recently have words more like artificial intelligence, narrative, interactive storytelling, games, and play, which corresponds a bit to these two labs that I've spent a bunch of time in. And correspondingly, I've named my lab the Principles of Expressive Machines, which is a mashup of the two labs, sort of the POP group, the Principles of Programming, and the Expressive Intelligence Studio. And what my mission is with this lab is to use principles from logic and formal methods to enable more expressive human-computer collaboration. To be a little more specific about what I mean by human-computer collaboration, I'm talking about applications kind of like these. Interactive storytelling was sort of my first foray, but I've also been very interested recently in intelligent tutors, conversational agents, and mixed initiative creativity tools. So mixed initiative is a term from AI that usually refers to an artificial intelligence process contributing to some creative activity in partnership with a human. So a lot of people, when I started talking about these applications, started calling me an AI person. When I worked on my postdoc at Santa Cruz, they said, "Oh, you're in AI," and I was a little bit confused by this statement because I've always thought, I'm a PL person. And normally when I hear AI these days, probably like you, I think of the more common data-driven statistical methods, known as machine learning broadly, that have sort of become the more popular way of going about most practical AI problems. The keyword being practical in a sense. So in these virtual settings where everything is synthetic, a lot of the classical AI methods that have a deep connection to functional programming are still quite prevalent. So that was, I think, what people were recognizing in what I was doing. One of the unifying themes underlying these disciplines is, of course, logic. And I love logic and use it in my work because I think of it as an excellent intermediate language between human thought and computational thought. When you express things in logic, it's precise enough that a computer can parse it and do something with it and reason about it, but it's also readable usually by a careful enough human. And logic, of course, is also great for reasoning about the kind of synthesized behavior and generativity that we see from processes. So another unifying theme is social reasoning. So instead of just strictly the types of logic we're used to, I'm really interested in how we can reason in a social manner. And that's both about sort of simulating sociological theories by creating virtual social agents, and also by thinking about all interactive applications, all software in a sense, through a metaphor of conversation between human and machine. So in this talk, so there's always this difficult thing with invited talks where you have to write an abstract before you've written the talk. And so my abstract may not entirely exactly line up with what I want to tell you, but I think that there's going to be some of that reflected in what I am going to tell you, which starts out with examining this common origin point between AI and functional programming, which involves some historical research on my part that I've quite enjoyed. And then I want to tell you about 3 research projects that I have worked on relating these two ideas. So first of all, from classical AI to modern functional programming begins, at least in my Carnegie Mellon biased view of history, in 1956 with Newell and Simon. So they developed this system called the logic theory machine. And they wrote this paper, The Logic Theory Machine, a Complex Information Processing System. And this was a theorem prover, essentially. They described a fragment of propositional logic and some processes for proving those propositions. And they thought that this was a groundbreaking exercise in computational, in computer science, because they were expressing forms of thought that had not previously been explored. They were exploring symbolically represented forms of thought rather than numerically represented. And this was really the first system to codify reasoning as a search process. They presented it at John McCarthy's AI Defining Dartmouth research project in the following summer. So I say AI defining because the term artificial intelligence hadn't been invented yet. It wasn't a thing that people said. But at this Dartmouth research project, McCarthy is said to have used the phrase artificial intelligence for the first time. And when we look back on this conference, AI historians like Pamela McCormick describe Newell and Simon's contribution as proof positive that a machine could perform tasks heretofore considered intelligent, creative, and uniquely human. And I want to really emphasize that creative part of what she's saying, that the reception to these ideas at the time was that logical thinking, sort of analytical thinking, the things we think of currently as a straightforward search procedure, were thought to be emulating creative thought. The paper also had a strong influence on functional programming. So I say they, actually, they hired a programmer, Clifford Shaw. Neither Newell nor Simon were programmers, which is something I learned while doing this research. But they hired a programmer who helped them develop a new language called IPL for the sake of implementing the logic theory machine. And IPL strongly influenced McCarthy's design of Lisp. And among some of its notable new features that had not been seen before were its use of lists rather than arrays, and hierarchical subroutines and recursion, which they identified as really being critical to the procedures that they were implementing. The use of repeated subroutines involved a level of nested function calls that really wasn't common in programming at the time. They later followed up this project with a paper called Current Developments in Complex Information Processing, where they're really talking about the programming process. And I don't expect you to read all the text on the slide, but they have a page in this paper which essentially outlines all of the features that they would like to have available when programming. And these are things that we identify nowadays as pretty much the standard of what a high-level programming language is. So there's things like we'd like to be free from specifying where information is to be stored, so we don't want to have to say where things go in memory. We'd like plenty of working space, so maybe they'd like a garbage collected language. We should be able to define new concepts whenever we find them useful. And basically they wanted to be able to express things at the level of the problem that they were trying to solve. So, following on with this whole idea of reasoning as search, I want to talk about 3 examples of it that I think are still active research areas today. Starting with, of course, the first one that Newell and Simon worked on, which is theorem proving. So I want to tell you about how the structure of these 3 problems is similar to one another and perhaps in an interesting way. So in theorem proving, you can think of the problem as giving this kind of input to a theorem prover, where you have one kind of input, what I'm describing by pointing at the turnstile in this diagram, which is the notion of consequence, the notion of logical derivation that you're defining, which is defined by the inference rules that you codify into the system and kind of assume are constant across iterations of the program. And then you supply 2 other pieces here. You supply your set of initial assumptions and your goal. And given this input, what you get out is a proof, if one exists, of the sequence, which is a composition of the inferences that you had defined when defining your notion of consequence. Likewise, there's a field called program synthesis, which was also quite active as an initial AI research area, in which I like to paraphrase Connor McBride here as having said in conversation since at least 2013, over and over again. Type inference is so last century. Let's keep writing our types and do program inference instead. And this is a particular flavor of program synthesis that's recently, I think, emerged and taken off, called type-based synthesis, where we treat a type as a specification, so usually enriched with some kind of dependency or refinement types. And then we supply a specification, we supply perhaps some set of library functions out of which we can assemble our programs, and we supply the typing rules of the language as something that's fixed as part of the language definition. And as a result, we can generate programs that satisfy our specification. So I'm also, for this work, I'm citing a couple of recent POPL papers from Osera and Pierce, type and example directed program synthesis, as well as Polikarpova et al. We're doing refinement type-based synthesis using something quite similar to this approach, where they're basically directly looking through the lens of propositions as types and thinking of it as a theorem proving sort of search problem. And then finally, the last bullet I want to talk about is a kind of behavior synthesis, how we generate agents that have particular behaviors in an environment, which goes back to the classical notion of AI planning. And in planning, again, you have a similar problem structure, wherein your notion of consequence, of chaining things together, is a set of primitive operators that you define, describing how an agent can change the state of the world. You have an initial state, which just describes how the world is set up in the beginning, and you have a goal state. And when you provide these things, a planner generates a plan, which is a sequence of operations getting you from the initial state to the goal state. And again, the common element here in the output is basically the relationship between what's generated as a composition of the individual units that you're defining in terms of your definition, right? So I'm describing all these things and trying to convince you, or at least I hope to convince you by the end of this talk, that these are all examples of creative machines. And again, you might think, well, these are just sort of standard search problems. But I really do think that the original intuition that people had about these processes as being creative, of finding mathematical proofs, of synthesizing programs that have certain behavior, is in fact evidence of creativity of a sort. And I'm not going to go into definitions of creativity and so on. You might find, if you find that kind of thing interesting, you might check out the International Conference on Computational Creativity, where they're really trying to get down to what do we mean when we say machines are creative. But these were early examples of things that people thought were creative, and I think that there are still unexplored aspects of them, such as how we derive insight in mathematical proofs that are really key to what we mean by creativity. So the first example of a research project that uses these ideas, and that I think will start down the road of explaining what I mean by creative search procedures, is looking at plots, basically narrative story skeletons, as plans or alternatively as proofs. So as I briefly described before, in AI planning, you provide a couple of things as input, and you get a plan as output. The things you provide as input are usually called a domain and a problem, where the domain is your set of operators or parameterized actions, and your problem is your initial and your goal configuration to try to solve between. And of course, the output is a sequence of those operators that get you from goal to initial, or from initial to goal. There's a standard set of languages out there that people kind of came up with in the 70s, I think, called PDDL and strips, which are domain-specific languages for planners, so basically specifying domains and problems. And actions are defined in terms of preconditions and effects, specified as logical predicates, and the configurations, the initial and goal configurations, are also collections of ground logical predicates. So this process of planning has been used in story generation, starting from sort of the turn of the millennium, I guess. Both Young in 1999 and Cavazza and Charles in 2001 explored the idea of using plans to generate plots. And I worked with my colleague, well, mostly Gwen Bosser and her colleagues Joao Ferreira and also Mark Cavazzo, one of the original people to use planning for this process, to sort of try to explore these ideas in the context of linear logic, which is a logic that's quite usable for many of the same purposes as planning. And in either of those situations, you can sort of look at the way you specify a story in a similar manner. So here's an example story, loosely inspired by Game of Thrones. So on the left over here, I've described the initial configuration and logical predicates, and on the right, I've given you a nice emoji-based representation of what's going on here. So for those of you unfamiliar with Game of Thrones, this is just kind of the beginning of season 1, where you have Robert Baratheon is king. He's allies with Ned Stark, who's currently the Warden of the North, and his hand has just died. So he's sort of in search of a new hand of the king. And he also has an heir, Joffrey Baratheon. In Game of Thrones, so in general, when you're describing a narrative domain in a planner, you usually want to describe your operators as kind of parameterized narrative events, sort of templates for how narrative events might unfold or occur in the course of the story. And in Game of Thrones, I figured it would be appropriate to describe operators as basically ways that characters can bid for power or be offered power and either succeed or fail at gaining power. Or perhaps lose power, right? So this is just one example of an operator in this domain, which is that the king can name a new hand, and you can see it has some parameters, ruler and new hand. And the preconditions are that we need the role of hand to be filled. The person who is the ruler in this operator is in fact the ruler of Westeros, and the ruler and the new hand are allies. And as a result, the effects we can describe as the new hand has been, in fact, offered this role, and then we also delete the fact that the hand needs to be filled. Of course, this idea of deleting facts is not quite logical enough, right? So to account for this in a sort of logical style, we need to use linear logic. And here I used asterisk for the tensor in linear logic and -O for the lolly. So this is the same rule, but it has some different defaults in how you describe it. So in linear logic, what's on the left-hand side gets replaced by what's on the right-hand side. So anything that you want to maintain, instead of explicitly deleting things, you have to explicitly repeat them on the other side to make sure that they occur after the rule has been applied. This is actually an important, this may seem like a quibbling distinction between these two forms of specifying rules, but remember this fact because it will come up later. Okay, so in either the planning or the linear logic formulation of these plot operators, what we have as a result is a compositional notation for plots. So we kind of have both a well, I'm going to say vertical and horizontal, but it actually is going the opposite way on the slide. We have a notion of compositionality in terms of sequencing our plans, and we also have kind of this horizontal notion of compositionality where we can talk about the way that different components of the state interact or don't. So for example, this first operator in our story, this first event in our story might be that Robert Baratheon names Ned Stark the Hand of the King, and as a result, Ned is in fact the hand, and then we also have the other two things that continue to be true. After this point, perhaps because Ned Stark is now in the same location as Joffrey Baratheon, the heir to the throne, he can now observe him, and something happens as a consequence of that. So you can see that that part of the state was not involved in the initial operator, but it's involved in the next step of the story. And so on. And then these other resources might go on to be used in some other aspect of the story. And what we can do, because this is a sort of compositional way of reasoning about it, is that you can think of this operator as defining an input-output interface. And then we can sort of draw a box around the whole thing and say, now we can summarize this whole story as season 1, episode 2, or something like that, and have an interface with which we can start to assemble this kind of Lego brick with the other Lego bricks of the story, where other things are happening separately and outside of this particular set of interactions. If you're curious about the algebraic properties of these sorts of structures, you can look into symmetric monoidal categories, or if you already know what those are, maybe you can think of it as an exercise to work out how this fits that pattern. So with the structure, I've given you sort of a notation for how the stories can be described, how the output can be described, but how we provide a goal for our planner is essentially just to provide a logical predicate that we would like to search for being the case at the end of the configuration. So for example, we could say, gee, it would really be nice if Ned Stark would just be king at the end of the season. And we can feed that in, and this is computer-generated fan fiction as a result. So this is actually the snippet of the output from my system, Scepter, which I coded up specifically for this example. On the other hand, though, so we have a nice way of kind of getting what we want out of a story. We can specify exactly what we want to be true and generate a story that makes it happen. But on the other hand, maybe we don't want to be so specific. Maybe we would like to instead allow the system to tell us things that might surprise us a bit more. So we could specify a varied ending or sort of a less specified ending with a logical formula that there exists a character where that character is the ruler of Westeros, and then basically try to simulate the Game of Thrones to figure out who might eventually win this bid for power. The problem with this, though, is that planners and theorem provers usually are great at finding efficient solutions, right? So if we want to show that there exists some C who has the role of ruler of Westeros, and our initial configuration is that Robert Baratheon has that role, then we might get a very boring story as a result. So that doesn't seem very creative, right? So stories in a sense are anti-efficient. We're trying to capture something about narrative structure here, and getting from a beginning point to an ending point in the most efficient way possible doesn't really reflect what stories are all about. There's usually some kind of conflicting goals. We think very much as humans. I think we think very much in terms of anthropomorphic aspects of story. The characters involved. The characters are driving what's happening in the narrative because they have goals that differ from one another's, and not both of those things can be true, so they have to resolve their conflict in some way. So my approach in what I worked on in my thesis, where I developed this linear logic-based programming language and showed that it could be used for specifying narratives and generating narratives, was effectively to sacrifice completeness of search in favor of variation in outcome. So I used a style of forward chaining logic programming that had non-determinism built into it. So it would, if multiple things could happen in the story, it would just choose randomly between them. And leaving the goals unspecified, this allows us to randomly explore the search space. So this just sort of sacrifices the whole idea of a goal in the first place. Of course, you could perhaps maybe get the best of both worlds by saying, well, we have a search process. Why not just enumerate all of the options, right? In most cases, narrative domains that are interesting enough to have varied output are also not necessarily terminating, so you might not have a well-defined set of all possible outputs. In some cases, though, you can actually do that, and there's prior work in which people have investigated every possible ending for a story specification. However, there's another limitation here, even if we think about relaxing our notion of goal, which is that kind of going back to this idea of conflict, right? Characters, actions happen in story events not just for random reasons, but for reasons that we as audience members would really like to be able to interpret in terms of characters acting intentionally, acting towards some goal that they have, and perhaps with goals that conflict with one another. And notably, this style of conflict also involves a lot of hidden information, a lot of beliefs that characters have that don't turn out to be true. That's where a lot of great stories come from. So for example, subterfuge, betrayal, and suspense all involve an element of information hiding and acting with limited knowledge. Meanwhile, so you may have noticed that I have talked about theorem proving and planning, but I've not brought up program synthesis. And over here, they have a similar kind of problem. So if you can't read the text here, it says, come up with an equation that is true when x equals 7. Be creative. You can make the equation as simple or as complex as you want. So here's a human failing at generating creative output. So this is a tweet from my friend and colleague Chris Mazinski, who works on program synthesis. So there's a similar kind of problem here, although this is, of course, sort of a joke. There are sort of real analogs to this problem in program synthesis. And one solution to this, or one kind of less than just straightforwardly naive way of specifying it, is to add constraints, to add enriched specifications, enriched types to what we want the output to be. So for example, you might be able to provide some input-output test cases as an augmentation of your type in order to be more specific about what you want the program to be able to do. This is just an analogy. There's not going to be something exactly similar to that, but what I would like to describe to you is a means of using constraints to enforce intentional behavior in characters. And to do that, we're going to move on to a slightly different research project on intentional reasoning. And at this point, I want everybody to take, at this point, I want to talk to you about game AI a little bit. So you might think of game AI as primarily being about, when you're bored on the computer and you don't have somebody to play against you, there's just a computer opponent that can maybe try to beat you at chess or Go or something like that. And in this case, the computer opponent doesn't need to make moves that are intelligible to you. It just has to be challenging enough so that you feel like you're getting something out of the experience. AlphaGo can play Go against a human and make moves that are totally mind-blowingly unexpected and inexplicable to the human, but that doesn't matter because it's still quite good at Go. On the other hand, a computer cooperator does need to have some kind of notion of intentionality. It needs to be able to express its moves in a way that humans can read as intentional. So to account for what we need for this, I'm gonna take sort of a massive step away from what you're used to thinking about and talk to you about a 1975 paper written by Paul Grice, who's sort of a logician linguist, and talk about the maxims of conversation, which I think at the time were just things he kind of pulled out of a hat, but they've later been empirically validated and so on. And these are basically simple heuristics for how to have a cooperative conversation, how to communicate with somebody in a way that you can both get across what you're trying to get across. And these 4 maxims of conversation are quantity, quality, relation, and manner. They've been defined in a way that's been sort of refined over the years, but just to sort of gloss what these are, quantity is effectively saying neither too much nor too little. Quality is not lying, essentially just telling the truth. Relation is staying on topic, making sure that whatever you communicate is relevant to what's at hand. And manner is avoiding sort of various things that Grice identified as manner, including, or as sort of etiquette disruptions, including obscurity and ambiguity. So we looked as a case study at, was there a question from the audience before we move on? No, okay. So we looked at this game called Hanabi, which is a cooperative card game, to study this notion of intentionality in computer cooperators. And Hanabi is a game wherein the traditional asymmetric relationship of knowledge in players is reversed. So instead of having a secret hand, you have a hand that everybody else can see, but you cannot see it, and you can also see everybody else's hand. You have a shared goal, which is to build solitaire-like decks in a common center of the playing field, which are sequentially ordered stacks of cards with different colors. The stacks have the same color. On a single turn, you can play a card from your hand. So suppose you've collected enough information that you know that it's playable, then you can play a card. If it matches the top of one of the stacks, if it's the next sequentially ordered card, then you succeed and it gets played. But if it doesn't succeed, then you burn through one of your limited number of tokens that when you run out, you lose the game or you end the game. Another thing you can do is discard. So if you don't know if any of your cards are playable, you can simply discard a card, and in return you receive another opportunity to give a hint, a token representing your ability to give a hint. And so the third thing you can do is give a hint, which spends one of these tokens. And hints involve telling one of your teammates something about their cards. And the something that you can give, the kind of hint that you can give is particularly specified as telling somebody all of a particular rank or color card that they have. So you have to tell them the total set of things within that rank or color. So for example, in this hand, this is the same hand repeated 4 times with a few examples of hints that are possible. So you can say you have 1 red card and point at the red card, or you can say you have 2 green cards and point at both, but you wouldn't be allowed to say you have 1 green card and point at only one of the 2 because they have more than 1. So for building a computational cooperator of Hanabi, what we need to do is model the player's knowledge, including our model. We also need to model their knowledge about our knowledge, right? They need to, we need to think about what they know about our hand to inform the way that we play. So we can give we give hints to human players in a way that we hope will be recognized as intentional. So what we do is we point out cards when it's unambiguous whether to play it or discard it. So you might, if both of somebody's 2s are playable currently, you might point out both of them. But if only one of them is playable, then you wouldn't want to point out both of them because it wouldn't be clear which one they ought to play. We refer to these 2 sets, or this set of 2 principles as underlying an AI agent we call the intentional model. And then we also include a 3rd one, which is sort of a meta-reflection of these ideas back on ourselves, where we're also not only interpreting hints in a way that we incorporate into our knowledge model to inform what card we play, but also as interpreting human players' intents as being given with the same idea of intent that we're using ourselves. And when we include that, we refer to that as the full model. So we implemented both this intentional and full model along with a baseline based on prior work, and did some experimental evaluation of these agents, one of which was just a simulation of the tournament, playing each agent as a cooperator with each other agent. And then we also did a human subject study where we were having just a one-on-one game with a human player and a computer player. And I want to just briefly tell you about some of the results of the human subject study. You can look at our SIG 2017 paper for more details on this. But you can see, so the orange lines here are the baseline, and then the blue and green are the full and the intentional. I won't get into the discrepancy between the full and intentional here, but I just wanted to show that, in fact, this is the way that the players scored, and they, in fact, perform much better when they're using more intentional agents. But not only that, they also, we gave them a survey afterwards on how enjoyable they found these agents to play with and how intentional they seemed. And that level of enjoyableness and intentionality corresponded with the level of intentionality that we implemented. So in some ways, that shows that our computational idea of intentionality does line up with a subjective interpretation of what intentional behavior ought to look like. So Grice's maxims of conversation again. How does this fit in? Well, quantity is saying neither too much nor too little. This is actually something enforced by the game rules, right? You can't give a hint that gives too much information or too little information. Quality is telling the truth. And in the context of this game, this is sort of an emergent property because it's a cooperative game, so players are incentivized to tell the truth. However, the final 2 are things that we're actually accounting for with our intentional model. Relation, or being relevant, is accounted for by only giving hints that can be interpreted as a play or discard, as play or discard instructions. You wouldn't give a hint that was irrelevant to the shared goal at hand. And finally, manner is avoiding ambiguity, which we do by only giving hints for sets of cards that are totally ambiguous. So this was a design that was specific to the game of Hanabi. It was not a fully general framework for intentionality, and as such, it has some limitations. One of which is that there's only one step of look ahead. And as I started this talk, of course, I was talking about search procedures, which we need to use to chain our reasoning. So how can we apply this kind of intentional reasoning to search? Well, the core observation here is that intentionality depends critically on belief. So we need a way of encoding knowledge in a more formal way so we can encode it in our specification. And we'd also like to be able to describe in a fully general way how beliefs might influence actions and vice versa. So this brings us to the final project on epistemic reasoning. So in epistemic reasoning, we codified an idea called theory of mind, which is another form of social reasoning that happens to coincide really interestingly with formal logical ideas. So theory of mind is forming mental models of other people's mental models. You can kind of think of this as everyone is like simulating each other's knowledge states, and those knowledge states, of course, will include that other person's knowledge state about you. So if you've ever noticed when you're in a conversation, you might be thinking about how the other person is thinking about you, right? So this is sort of a nested knowledge idea that is borne out in social sciences as a key form of social reasoning in humans. It's thought of as correlating with how socially successful you are, how well socially integrated you are, whether you have this skill, this ability to form theory of mind. It's also easily explainable with jokes. So you may have heard this three logicians walk into a pub joke where the bartender asks, will everybody have a beer? There are three logicians. The first one says, I don't know. The second one says, I don't know. The third one says, yes. Okay, good. I'm glad you all know the joke.
Says which beer?
Right, yeah, I know. So of course they're all modeling each other's knowledge, and at each of these steps, nothing is changing about their preferences for beer or not, or anything else about the world. What's changing is the epistemic state, right? They're changing what they know about what other people know, and this influences their ability to communicate knowledge. Okay, so what we need to encapsulate this is a kind of epistemic logic in which we can describe knowledge or truth relative to a particular agent. So we use a box modality indexed with an agent lowercase a, and we say box of A of capital A refers to an agent little a believing a formula A. Additionally, though, because these epistemic states are changing, we need a notion of a formula holding under a sequence of epistemic actions. So we also have actions alpha and a modality describing when a statement holds under these actions. So this is a form of dynamic it's a form of dynamic logic as well as a form of epistemic logic. These actions are things that may change the actual underlying world, as well as changing the knowledge state, i.e. changing the set of worlds that an agent considers possible. So to be more specific about what these actions are, we take a formulation from Baltag in 2002, which was suitable for our purposes, wherein there's a single primitive idea of changing the underlying actual world, which is this flip operator. Which they formulate propositions in kind of a very classical Boolean fashion. So they're able to just say, well, change the truth value from true to false. That's our notion of change in this world. An action can be a precondition, and the meaning of a precondition is essentially that if the condition fails to hold, then the rest of the action will stop and not execute. There's a non-deterministic choice in which either one of the two actions fires, and then there's sequencing of actions. In addition to these, there are actions that strictly affect the epistemic state. So an action with a superscript of an A or an agent or a set of agents will be effectively saying the agent A perceives this action to be occurring or believes that this action is occurring. On the other hand, there's a notion of a public action, which is both truthful and mutual in the sense that it does actually change the world with that particular effect. And then it is known by all agents to have happened, and all agents know that each other know, and so on recursively. So to account for what these things actually mean, we have a notion of an epistemic state, which accounts for a set of worlds that from a given actual world, each agent considers possible. So there's sort of a Kripke-like accessibility relation. Excuse me. So there's an actual world, there's a set of worlds that an agent considers possible, and then there's a notion of how the set of possible worlds for each agent expands and contracts based on the actions that occur. So if we apply an action alpha, we have to compute how alpha applies to each of the possible worlds in every agent's knowledge state. And this will look differently for each action alpha that we have. So for example, to apply an action alpha plus beta as a non-deterministic choice, then what happens in the actual world is that we either evolve to alpha or to beta, but the set of worlds that the agent considers possible, if this is what they're perceiving as happening, is that we simply double the number of possible worlds. We apply alpha to all the worlds we consider possible, and we apply beta to all the worlds we considered possible, and now all 8 of those are considered possible. Just for one other example, the precondition rule. So this is an example that shows how we can proliferate our set of possible worlds. We can also contract our set of possible worlds. For example, if there's a precondition on an action that rules out certain worlds from being possible in the first place. So if we have a precondition that says we have to either be in the blue or the red world, and then we can proceed with alpha, then this eliminates the 2 worlds in the middle of our set that are not blue or red, allowing us to reduce our uncertainty. Now we're more sure that things are a certain way because of something that happened. So if that was a little bit too abstract for you, you can think of in terms of a particular Game of Thrones villain-type character, and that what we're doing is simulating Littlefinger's style of thought, right? Fight every battle everywhere, always in your mind. Everyone is your enemy, everyone is your friend. Every possible series of events is happening all at once. Live that way and nothing will surprise you. Everything that happens will be something you've seen before. So I apologize for any AI supervillains that emerge as the result of this work. Okay, so we've got this tiny dynamic epistemic logic. Reminder, this was a prior work by Alexandru Baltag. And in this core calculus, we can express some tiny examples, like if we flip a coin, then we have a non-deterministic choice between Alice, the person who flips the coin in secret, knowing that the coin came up heads versus knowing it came up tails. And everybody else who's observing the action but can't see the result of the coin toss perceives a non-deterministic choice between the two. Unfortunately, it's hard to give an example more complex than this because of this very primitive idea of simply flipping truth states around. So what we did, what my PhD student Marcus Egger and I did, was develop a more practical sort of action language on top of this kind of core theory and compile it down to Baltag. So we still get the epistemic reasoning that we want, but we can express things in a slightly more natural way. So this is just a couple comments about, like, if you tried to do everything in Baltag, you can use their notion of aggregate sums and products to express these changes that are more complex than Boolean flips, but you get a huge term size blow up when you do it. So instead, we described an action language where we have parameterized actions and a enriched command language. Where this command language includes the ability to set, basically assign values to properties and to sequence commands as before, but also the epistemic operators are now formulated in a slightly higher level way. And in particular, I want to look at this learn construct in which we say that a group of agents learns a particular fact, and the kind of fact that they can learn is mostly familiar logical propositions, but also a sort of epistemic quantifiers each and which I want to tell you a little bit about. If we were just to use the standard existential quantifier to try to figure out what card is at the top of a deck of cards, this would actually be completely useless knowledge. So it's not useful for us to know that there exists a card at the top of the deck in the sort of, of course, in the classical formulation, it doesn't provide a witness. We don't know which card it is, right? So we have a notion of epistemic quantifier. Again, this is expressible in terms of Baltag, which tells us specifically which C it is, which reveals the knowledge. And similarly, analogous to for all, we have an each operator, which allows us to finally express a legible example in terms of the previous work, which is the hinting a color in Hanabi, where you have a player and a color, and we can express this as the player is learning each index of their hand that matches the color that we're given. So we implemented this compiler in Haskell and actually benefited quite a lot from the language. We had a sort of higher order representation for possible worlds and used laziness in order to save some, in order to be able to represent that effectively. Our language provides an ability to specify these operators as well as sequences of actions that you can query at every step. So you can examine the epistemic state between every action you execute. So one of the first things we did actually was codify the logicians in a bar joke and evaluate, yes, we can in fact see what each agent learns after every utterance in the joke. Yes, and in addition to that, some of the new ongoing work is that we're also able to specify goals that can generate sequences of actions so we don't have to write them by hand. And thus, finally, we can get to narrative generation again and talk about how to specify story worlds which have emergent intentional behavior. So I am switching over to a bit of a detective story kind of setting in which Sherlock is either at Baker Street or Scotland Yard, and Moriarty doesn't know where Sherlock is. Of course, Sherlock knows where Sherlock is. So we have two possible worlds, World A and World B, in one of which Sherlock is at Baker Street, and it looks to Sherlock like that world is the actual world, including all three of those things, right? But it looks to Moriarty like it could be World A or it could be World B. And World B is simply symmetric, where Sherlock's in Scotland Yard. If this world were in fact the case, then Sherlock would know that it's the case, so he knows the whole world. And Moriarty still, oh, that's a typo, apologies. Moriarty still believes that World A or World B is possible. We can also set up the operators in this world, which are not particularly interesting. So instead, I want to just bring you to the goal specification, which is we can say something like, well, we want an end state in which Moriarty has murdered a victim, and Moriarty believes that Sherlock believes that there exists someone else other than Moriarty who murdered this victim. And what we get when we specify this, this kind of story outcome, you can maybe think through it in your head, is a story in which Moriarty frames someone for a murder. Okay, so that's most of my own personal work that I wanted to tell you about, these 3 investigations into using logic for games and storytelling, generating narrative with planning and linear logic, intentional reasoning in cooperative games, and codifying intentionality with epistemic logic. So to conclude, I wanted to kind of call back to some of the points that I mentioned in the beginning on functional programming and AI, and talk about how we might be able to continue to explore and enable richer applications. So to me, compositionality is functional programming's secret weapon. You know, it's not on the bingo card, but I think that's maybe just because it's the free space, right? Like it's, you know, it's in everything we do, right? So and we don't necessarily always write it down formally. So I wanted to show you one notion of it, a sort of Frege's principle version, which is just that we can make sense of the meaning of composition of A and B for any particular notion of composition we want to talk about, strictly in terms of the composition of the meaning of A with the meaning of B. And perhaps we also need to interpret our composition operator in terms of meanings. What this is also saying, though, is that, of course, we have, for all the domains that we're interested in, we are able to formulate a means of putting 2 things together in a way that we can make sense of in terms of the original 2 things, right? So, of course, we have function composition, where the notion of meaning here is actually an interface. So to make sense of how we can compose 2 things, they have to match at the interface, right? So a function that computes from x to y and from y to z can be composed, and then generate a new interface, which goes from x to z. In Theorem Proving, we also have a notion of compositionality, which is in fact thought to be the definition of what it even means to be a logic, in which the notion of consequence is, in a sense, transitive, is able to be composed. So the way we compose a proof of A from a set of assumptions gamma, and a proof where we need an assumption of A, and from that can get to a conclusion of C, is to, again, conjoin the interfaces, where the sets of assumptions we had originally, apart from that joining piece, get composed with one another. And finally, in planning, I want to talk about the sort of horizontal composition principle that's present here, which is a sort of frame principle, which you perhaps are familiar with from things like separation logic and so on. So planning also, and AI in general, cares about this notion of a frame principle in which you can talk about actions that are happening independently of one another so that you can augment your state with things that don't matter and then know that your original plan still works. So if you have a plan pi that takes you from a state delta to delta prime, and a plan rho that gets you from state gamma to gamma prime, and the pieces of gamma are not used in pi and the pieces of delta are not used in rho, then ostensibly you should be able to sort of parallel compose them, right, to get a composed plan in which you have the conjoined state as your initial and the conjoined primed states as your final. But interestingly, the way that planning was originally specified, so this is going back to that thing that I mentioned in the beginning, the delete operator, right? So the delete operator in the effects of a planning the delete construct in the effects of a planning operator allows you to delete facts that don't appear in the preconditions, which is a bit of a strange thing. And in fact, it breaks compositionality, because if some part of plan pi deleted a condition that didn't occur in the prefix of pi, but it did occur somewhere in gamma, then suddenly this plan would no longer be possible to execute, or the bottom plan would no longer execute the same way. So it turns out that using a logical basis for describing actions is what we need in order to get this form of compositionality. And to me, this is sort of a clear win for using compositionality as a grounding point, as a sort of design principle, rather than sort of making up ad hoc formalisms. So in the future, some research challenges that I would really like to see addressed, and in particular, if any of you are looking for collaborators or perhaps a PhD position somewhere, I would love people with training in functional programming and formal methods to work with me on some of these challenges. Some of them are, so one of them is this notion of dynamic logic in general. I think we usually take it as a given that a dynamic logic is indexed with a style of program that's very imperative. So you may have noticed that this dynamic epistemic logic used imperative state updates, and that's no good, right? Like, we can do better. So I think it would be cool to explore functional action languages or maybe linear logic-based action languages and see if we can apply some of this dynamic logic theory to those. And finally, and second, this dynamic epistemic logic, in addition to being imperative, is also classical. It's sort of critical that you be able to reason about a closed world of states so that you can reason about what's not the case. And I don't think that makes it impossible to come up with a constructive formulation, but it doesn't seem immediately obvious to me. And if we wanted to come up with some kind of Curry-Howard interpretation of it, then we would need to do that. So I think it would be interesting to explore whether that's doable. And then finally, since I've been talking about this metaphor of communication and conversation between humans and computers, I think it's interesting that we've also been making some strides in session types, which are a way of formulating conversational protocols between agents or processes, whichever one you want to call them. And I think it might be interesting to try to augment those types, which are based on linear logic, with some kind of notion of epistemic reasoning, perhaps to formulate information flow sorts of theories. So I called this talk Compositional Creativity. The creativity part is really because I think we're talking about generating insights, behaviors, and narrative. And all of these forms of reasoning, I think, are really crucial to what people talk about when they mean creativity. So there's a whole community of folks who work on computational creativity, and the compositional part for me refers to basing this on logical specifications. And finally, I wanted to leave you with sort of an answer to this question: why have I gone and investigated all these applications based on games and stories? And it's really kind of for the same reason that I love logic. It's that we've been using play and storytelling as a means of communicating throughout all of our history, even before we invented logic. And logic has served us very well as computer scientists as a basis for exploring new computational abstractions. So perhaps play and stories can do the same thing. I think that they're really rich sources of abstract ideas, and the best abstractions are discovered across diverse disciplines. Thank you very much.